In today's video, we are going to look at what happens when we try to add or subtract radical expressions. And we're also going to look at a few examples that have us multiplying conjugate pairs and multiplying with those radical expressions as well. But the biggest thing that we need to think about when we are adding and subtracting radicals is we have to think of this in terms of like terms. So just like I could add 2x plus 4x, but I couldn't add 2x plus 4x squared, I need to make sure that I have exactly the same index and radicand in my terms. So for example, in number 1, if we're going to simplify this expression, you'll notice that both of these expressions have a square root 2. So they have exactly the same index of 2, and they have exactly the same radicand, our number under the radical, which is 2. So that means I have exactly like terms, and I can just add my leading coefficients, in this case, the 4 and the 2, and put these together to make the expression 6 root 2. And so we will come across some problems, for example, number 2, where we don't, on first glance, have the same radicand. So we have an 8x squared y under 1, and we have a 2y under the second. But if we use the ideas from our previous 2 lessons, we can actually reduce out or simplify that first radical. And perhaps we may have the same radicand after we do that. So with the 8, again, keep in mind our factors of 8. I'm going to write this a little differently just based on the amount of space that we have. Our factors of 8, I have a factor of 4, which is a perfect square, and then a leftover factor of 2. So when I'm simplifying out, well, I know the 4 simplifies out. Perfect square root of 4 is 2. I can also do this with, and I've used that one now. I can also use the x squared. Well, perfect square root of x squared is just x. But that leaves that leftover 2 from the 8 and the y that didn't simplify out from that first expression. Now in my second expression, I can't do anything extra, so I'm just going to copy that down. And now I'm noticing that my 2 radicands are exactly the same. I have root 2y in both terms. So that means I can go ahead and combine my terms, and that means I'm just combining my leading coefficients pretty much. So we have a 2x minus x, which means we have 1x left over. And then our kind of variable for the expression is the square root 2y. Alrighty. So number 3, same thing. We don't see, it doesn't look at first glance like we have exactly the same radicand in every scenario. But let's simplify these out and see what we end up with. So 18, again, as I'm always going through these, I'm always thinking about what are my perfect squares, that would simplify out this expression. For 18, I know that's 9 times 2. For 8, I know that's 4 times 2. And for 72, if I do a little bit more math, I know that's 36 times 2. And why do you think I picked out the 9, the 4, and the 36? Well, those are all perfect squares, so I know I can simplify those out. So if I rewrite this, and I'm going to do this in 2 steps. We originally had a 6, and then when we take the square root of 9, we'll end up with a 3, but we had the leftover 2 that didn't simplify. In our second term, we already had a 4 outside. We have square root of 4, which goes to 2, and then our leftover 2 that didn't simplify. And in our last term, we already had a negative 3. We can take the square root of 36, which is 6, and we have a leftover root 2. And so then combining my like terms, or multiplying out in the front, simplifying this so it's a little neater, we really have an 18 root 2 plus 8 root 2 minus 18 root 2. Wait a second. We have an 18 root 2 minus 18 root 2. Those simplify out. They cancel each other out. And the only thing we're left with is the square, or 8 times the square root of 2. And again, we wouldn't have known that all of that simplified out if we hadn't simplified the individual radical expressions within the problem. Alrighty, let's check out our next one. So now we're looking at number 4. And at first glance, hey, I have radicals with 3's under them, but one of them is different. So our second term, 5 times the cube root of 3, is just slightly different than the other 2. I can only combine my 8 root 3 and my 6 root 3 because they have both the index and the radicand exactly the same. So if I combine those, I have a positive 8 and a positive 6, so that's a positive 14 root 3. And again, I'm just treating the root 3 kind of like a variable, like it was an x. And we can't do anything to simplify that extra term, so 5 times the cube root of 3. And do be careful when you're writing out these kinds of problems, because you don't want to accidentally write this as like 5 cubed times the square root of 3. Where you put your index is important, so there's nothing wrong with spacing it out a little bit if you need to. So now looking at number 5, this one's getting a little bit more complicated. I notice every single one of these has a cube root, but none of them look the same. I'm going to have to do some simplifying, but also too, I'm noticing some of these values are a little bigger. I have like cube root of 24 and cube root of 128. So while I'm simplifying things, it's going to be very helpful to know what my perfect cube roots are, to see if that might, help me simplify these out. So off to the side here, I'm going to go ahead and write out my perfect cube roots. I got a little room actually from number 4. Well, 1 cubed, we can include it in our list, but it really doesn't make a difference. We have 2 cubed, which comes out to be 8. We have 3 cubed, which comes out to be 27. 4 cubed, which comes out to be 64. 5 cubed, which is 125. 6 cubed, which is 216. And the reason I went that high is because I was seeing that 128 and I wanted to see if that popped up in my perfect cube roots. It doesn't. And same sort of thing with the 24. But are any of those perfect cubes on there factors of those values? Well, 24, I know that's 8 times 3, so I can still factor out a perfect cube from there. 128, if you do a little bit of math, you'll notice that 128 is actually 64 times 2. So again, we'd have a perfect cube that we could take out of this. And so I'm going to write this one kind of similarly similar to, number 2, where I was just putting my factors down in the line, just so I can keep track of where things are. And again, the more practice you have on these, you might start being able to do some of these in your head, but until you're really, really comfortable with them, write out your factors, space out your work. There's nothing wrong with taking a little extra room on some scratch paper, and you can always recycle the paper when you're done. Okay, so if I'm looking for cube roots, I'm looking for groups of 3 factors that I could simplify out from that radicand. So I can't do anything with the 2, but my x to the 7, I can rewrite him as x cubed times x cubed, and we have 1 left over x. So I do actually have 2 perfect cubes that I could take out of that. Y to the 9 is really y cubed times y cubed times y cubed. 3 perfect cubes I can simplify out. Okay, 24, I can rewrite that as 8 times 3. And again, 8 being one of our perfect cubes, so that's going to help us out. X cubed is already a perfect cube. Y squared, I don't have any multiples of 3 factors that I could take out. 128, and again, I'm crossing this out. I don't want to accidentally forget that I factored out that 128. He's really 64 times 2. And so 64, again, one of my perfect cubes on my list. X to the 7, just like before, I know that I can change him to x cubed times x cubed times x. And y to the 9, same thing as in the first one. So I'm thinking I'm probably going to be able to simplify the first, or combine the first and the last terms, that those are actually going to be like radicands, but I might not be able to do that with the second one. So let's see what happens. So simplifying out, again, I like to write out each factor just to help me organize my brain a little bit. So let's see, in this one, we don't have any numbers out front already. We can, let's see, I'm going to actually change colors. We can take out an x cubed, perfect cube root of x cubed, but we can do that twice. So we're going to have an x squared outside. We have 3 perfect y cubes. So 1, 2, 3, which means we can do a y cubed on the outside. Therefore, we have leftover inside our cube root. We had a 2 and a leftover x, and that's it. Everything else got simplified out. Alrighty. So then, Again, nothing in front of the term. I can take out perfect cube root of 8, which is 2. Perfect cube root of x cubed, which is x. And then everything else stays inside the perfect cube root. We had a leftover 3 and a leftover y squared. Okay, last term. Again, perfect cube root of 64 is 4. We can take out the x cubed twice, so x squared. We can take out the y cubed 3 times, so y cubed. But then left over inside our cube root, we had a leftover 2 and an x that didn't get simplified. And so now pausing and looking at what we have so far, my first term and my last term both have a cube root of 2x. They also both have an x squared and they both have a y cubed. So those are absolutely like terms. We could combine those. But we can't do that with the middle term. Nothing else has a cube root of 3y squared. So he's going to sit by himself, but we can combine these. And really the only difference is our last term has this 4. How many of them do we have in the first term? Well, we've got an implied 1 in the front. So really we have 5 of those. So 5x squared y cubed times our cube root of 2x. And then we had our leftover minus 2x cube root of 3y squared. And again, this problem is probably a little bit harder than anything we're going to ask you to do. But if you understood going through the steps on this one, then you can attack anything on these. All right, so the second piece of this is we need to look at something called conjugate pairs, and we're going to be multiplying binomials with some radicals in them. So let's attack number 6 first. And so looking at number 6, it looks kind of like we had something before. So actually off to the side, I'm going to do a 3 plus x and 1 plus x. And actually, let's do that multiplication first just to see how it matches up. So if we distribute out, we'd have a 3 times 1 plus a 3 times x plus a 1 times x plus x squared, otherwise known as 3 plus 4x plus x squared. So let's see how that looks similar to putting that root 5 in place of that x. So again, distribute carefully. So 3 times 1 gives me 3 plus 3 times our square root of 5, aka just 3 root 5. Again, we can't multiply the 3 and the 5. One's under a radical, one's not. Then we have root 5 times 1, so just plain old root 5. And then we have square root of 5 times square root of 5. And I'm going to go ahead and write those multiplied out just so you can see all my thought process. So first thing I notice is I have that square root of 5 times square root of 5. Well, isn't that really square root of 5 squared? And let's see, doesn't square and square root, shouldn't they undo each other? They're kind of inverse operations. So really, square root of 5 times square root of 5 is just 5. Again, something we talked about when we were multiplying radicals in lesson 7.1. Okay, so now any like terms? Well, I've got 2 just straight number values, and then I have 2 values that both have that radical 5. So combining my like terms, I've got an 8 plus, and again, how many root 5s do we have? Okay, we're implied 1 with that second term, so it's 4 root 5. So the process is really not all that different as if we had an x in there, but we do need to be careful with simplifying. So it's kind of like when we were looking at the square root of -1 or our I values. Until we get to like the second or third step, just treat it like any variable and then do your simplifying. Alrighty, so 2 more problems. Here we go. So this is where this thing called conjugate comes in. So we talked about these before when we did imaginary or complex numbers. So for example, we had like 1 plus 3i and 1 minus 3i that would be conjugates of each other. All we're doing is changing the sign. And so when we multiplied those before, when we were doing our quadratics unit, the neat thing that we found is that we had a lot of things that canceled out. So we're probably going to have the same kind of thing happening with this. The only difference is we're using radicals instead of imaginary numbers, but they're still, the only difference is that opposite sign. So we can still call them conjugates. So let's see what happens when we distribute. So we have 2 times 2 is 4, 2 times a negative root 3. Then we have root 3 times a positive 2, so positive 2 root 3. And then positive times negative, which is a negative, root 3 times root 3, which is basically root 3 squared. Except what's root 3 squared again? Now you square a square root, and it comes out to just that value. We have a negative 2 root 3 plus 2 root 3. That simplifies out. So we're really just left with a 4 minus 3, and this whole expression comes down to 1. Now this is only going to happen when you have perfect conjugates. So if we have something like in number 8, it's not going to act exactly the same. And 8's really a different problem in disguise. When you have anything squared, what does that really mean? In essence, what does that exponent 2 tell you to do? Well, really, we're just multiplying something by itself again. So this is really 5 plus 7 root 3 times 5 plus 7 root 3. Again, you can't just distribute the squared. You have to multiply out the entire expression. You'd get totally different answers out. And this is the one that is going to be correct. So then distribute out. 5 times 5 is 25. 5 times 7 root 3 is 35 root 3. And then again with your inner terms. And then we have 7 root 3 times 7 root 3, or 7 root 3 squared. And so on this last term now, because I don't have any plus or minus signs in there, I'm really just squaring the whole piece. So 7 root 3 times 7 root 3, which means we can multiply the 7 times 7, aka 49. And square root of 3 times square root of 3, well, that just comes out to 3 again. And so this whole term actually simplifies down to 147. So here are like terms. We have 147, we have 25, and then we have our 35 root 3's in the middle. Combining our like terms, 25 plus 147 is going to give us a 172. And then 35 root 3 plus 35 root 3 gives us a 70 root 3. And notice when I'm writing out these expressions, I tend to put that radical expression second. Mathematically, it really doesn't matter, but it's the same kind of notation how I always left the imaginary number second. It's just the conventional way of writing things out. So, I'm going to end the video here. However, check out the You Try problems. So we have 4 problems. Let me scroll down so you can see them on the screen if you haven't printed out your copy. And so here are your You Try problems. I'm going to stop the video here, but once you've tried these out, check the filled in version to see how you did on these problems. Let me know if you have any questions before you attack your practice or your mini quiz.